We stated earlier that for a reversible process that the entropy change is going to be 0, and for an irreversible or spontaneous process the entropy change will be greater than 0. So for this inequality, which defines the second law of thermodynamics, ds is greater than or equal to dq over T, the differential of heat over temperature, for giving us the differential of entropy, that equality case ds would be equal to the heat of a reversible process divided by the temperature. So claiming here that we have a 0 entropy change for a reversible process, let's go through the two examples of reversible isothermal expansion and compression and reversible adiabatic expansion or compression to see that this really is the case for those two processes, just to demonstrate that this is true. Okay, so we're going to start out with reversible isothermal expansion. Remember, isothermal, the temperature staying the same across the entire process. So some reversible isothermal process. All right, our total entropy change, delta S, is going to have two parts. We're going to have delta S of the system plus delta S of the surroundings. That will give us the delta S of the universe, which is an isolated system, so the entropy change must be greater than or equal to 0. And let's see that it's 0 for the universe. And as I said, T is constant for any isothermal process. Okay, so our delta S, since T is constant, can be defined as the heat of the system over temperature. That'll give us the entropy for the system plus the heat of the surroundings over temperature. That'll give us the entropy change of the surroundings. And as we said for a couple of videos ago, for the expansion or compression of a gas, the entropy change for that process, we derive that ends up being nR log V final over V initial. But let's remember that whatever the heat of the system is, the heat of the surroundings is equal and opposite to that. So, and they're also going to be at the same temperature there. So that is going to mean that the entropy for the surroundings, which is input, or which is going to go down if the system expands, or it's going to go up if the system compresses, the opposite case. Those two are going to be equal and opposite, and they're going to sum up to 0. So this is only true because that was reversible. If we did that in a reversible way, then there would be more work done and there would be less heat input, and so this value wouldn't be as large and it wouldn't cancel out. But this value only is as large as this value when it's done reversibly, which is doing the minimum amount of work during an expansion and doing the maximum amount of work during your compression. And again, that was true because during this isothermal process, Q sys equals minus Q surroundings. So our net is that delta S equals 0. All right, and for the other case, not sure why that keeps coming up red. For the other case, reversible adiabatic expansion, or compression, expansion, compression, process, pick your favorite word. We said that for that case, we're going to have Q equals 0. So Q system and Q surroundings are both going to be 0. So the net result there is that delta S, which again is the sum of the system entropy change plus the surrounding entropy change, is going to be 0 over T, because that Q is 0, plus 0 over T. And of course, 0 in both of these numerators here. That is going to give us a net of 0. So our delta S is going to be 0. And this confirms that for both of these processes, both of these reversible processes, they confirm that what the second law predicts, this equality that ds equals 0 for a reversible process.